With over 5 million miles of fiber optic cable and power lines across the United States, telecommunication and power lines often span environments with varying safety conditions, like crossing over mountains or through forests. The Common Ground Alliance reports over 400,000 accidents related to utility lines annually, with some capable of causing deadly disasters like the 2018 Camp Fire in California or the 2023 fires in Hawaii.
As a result, telecom infrastructure must comply with regulations governing line sag, ground clearance, and equipment condition. Currently, auditing methods rely heavily on manual measurements and in-person inspections, which require significant time and labor. Commercial solutions cost thousands of dollars annually for hardware and software licensing. Our project addresses the need for a more cost-effective, repeatable, and efficient method of verifying infrastructure compliance through automated sensing and data processing.
I'm Lee Fielding, and I'm the team and optics lead.
I'm Richard Pang, I'm the procurement and mechanical lead.
I'm Nathan Vance, I'm the software lead.
I'm Jacob Gordinsky, I'm the firmware lead.
I'm Jacob Green, I'm the electrical lead.
I'm Lucas Vaichunas, hardware and testing lead. Our solution is a handheld prototype which demonstrates the feasibility of a cost-effective mapping and inspection device that maintains the performance of commercial products at a fraction of the cost. Our prototype validates accurate assessment of telecom line sag, ground clearance, and equipment identification through the use of a combined LiDAR and camera system and a whole lot of data processing. Our system is on the cutting edge of current technologies, thus creating requirements was one of our biggest challenges. Our most important high-level functional requirements are: the system shall collect 3D spatial data of telecommunication systems, the system shall measure aerial telecommunication line sag and attach it as metadata, the system shall identify different telecommunication poles, crossarms, lines, and pedestals, and the system shall provide GPS location of scanned telecom equipment. With these, we then created specific system requirements to be met by our system and determine their appropriate verification methods, as seen here. Some notable quantitative system requirements ensure that our hardware systems would be useful in the field, such as identification accuracy, where the system shall achieve 65% success in identifying poles, crossarms, and pedestals within 5%. Measurement accuracy, where the line sag and ground clearance measurements shall be within 5% of ground truth. The system shall be battery powered and capable of 15 minutes of data collection. And the system shall weigh less than 10 pounds.
To meet set requirements, we conducted a Pew matrix analysis for a hardware solution to complement our future software pipeline. After major considerations such as cost, availability, object identification, and measurement accuracy, we settled on a camera and LiDAR fusion system, where LiDAR would be able to provide accurate depth information and the camera would be able to provide semantic information. To mount all of our hardware components together, we conducted another Pew matrix analysis, eventually opting for a handheld design, which would reduce the complexity and reduce the cost as compared to a potential drone solution. This also allowed us to focus on the software aspect of the project, which is much more important. You might also notice that we have no mechanical engineer on our team, and thus complex mechanical designs were mostly ruled out.
Despite landing on a general hardware solution, choosing the correct LiDAR and camera for our project remained difficult. We went through many LiDARs, with some not meeting spec and some landing dead on arrival. After much struggle to find our chosen LiDAR, we did a quantitative analysis to ensure that what we bought was exactly what we needed for our project and would not become a bottleneck for our software pipeline. Let's get into the analysis now. For LiDAR, we performed a radiometric analysis to compare sensors based on their ability to detect thin, low reflectivity, 1 centimeter power lines at large standoff distances. For our chosen LiDAR, the LiVox Horizon, the red region marks our expected operating range for typical telecom and power lines. The analysis shows that we can collect enough data in just a few seconds to accurately reconstruct power lines in 3D in order to compute line sag and ground clearance. For the camera, we performed radiometric and motion blur analysis to ensure that we could use adequate exposure times without overexposure or single pixel motion blur. At a standoff distance of about 16 meters, we found that an exposure time of around 5 milliseconds with a medium aperture size gives strong signal-to-noise ratio while staying below 1 pixel motion blur. We also wanted the camera and LiDAR fields of view to align closely for sensor fusion. Our final setup achieved that well, with a LiDAR vertical field of view of about 25.1 degrees and a camera vertical field of view of about 23.7 degrees. Overall, this analysis gave us confidence that our hardware could support the rest of the system.
In our post-processing software design, we utilize the data captured from the LiDAR and camera together to measure ground clearance and line sag and label telecommunication components. Our software pipeline contains the following key components: image segmentation by YOLO V11, wire extraction and line fitting software built off and expanded upon an open source project called 3D LiDAR, and lastly a camera, LiDAR, and GPS fusion software, utilizing open source FastLIO and our own homebrewed code. When designing our system, we made several key decisions to ensure flexibility, usability, and compatibility across different environments. First, we chose to use Docker and WSL for pre-processing, since tools like ROS and FastLIO are only stable on Linux. This lets us maintain reliability while still keeping the overall system portable across different machines. We also designed the pipeline as modular stages, allowing users to skip steps, retry specific stages, or use external tools if needed. To support different hardware setups, we included both local GPU processing and a Google Colab fallback, so users aren't limited by hardware constraints. Finally, we built a Windows-based GUI to orchestrate everything, providing a familiar interface and easier integration with other tools.
Taking a closer look at our handheld device, we see our LiDAR, camera, LiDAR converter, and an integrated battery in the handle. And now, looking at our computing, we have an onboard Raspberry Pi with storage ports satisfying a system requirement, LEDs satisfying a system requirement that show the status of the device, mode switching buttons, on-off switches, and finally the total weight of our handheld device is 5.4 pounds, satisfying another system requirement. Now let's go through a quick demonstration of how to use the system. First, you'll turn on the master switch and then the LiDAR switch, select your mode using the blue button, and then click the green button to begin a scan. Then, once the LED turns green, you point the camera at the object of interest and allow yourself to move through the scene, capturing all objects of interest within the camera frame at some point and covering everything that you want with the LiDAR. That includes poles, cross arms, transformers, wires, and crucially, ground points, because the post-processing requires everything in order to work. To complete a scan, simply click the green button one more time, allow the Pi 15 seconds to save all your data into a file, flip both switches off, and then you can remove the USB storage device, plug it into your laptop, and begin post-processing.
Now I'll walk you through a quick demonstration of the post-processing workflow. First, we select a scan ROS bag from the onboard USB drive and give it a name. Then, we click Run under ROS bag preprocessing to extract the data needed for fusion and wire extraction. Next, we line the image poses using the timing viewer, adjusting the time offset until the images line up with the point cloud, then we save the offset. Following this, we filter the point cloud to reduce processing time and sharpen features such as power lines. Finally, we apply a bounding box to the region of interest. After that, we run image inference to detect objects such as poles, pedestal boxes, crossarms, and transformers in the images. Once inference is complete, we run fusion. The software will project those detections into the point cloud and identify the corresponding objects. As the last processing step, we run wire extraction. We can click View Result to inspect the labeled point cloud. The semantic viewer shows both fused objects and line metadata such as sag and ground clearance. Finally, we open the leaflet viewer to inspect all identified objects on the map. Selecting an object shows its metadata and associated images, and false detections can also be deleted there. Overall, we've shown that we can successfully capture and analyze utility infrastructure using our hardware payload and software package.